Okay, well, we'll go in and get started. I know a few folks are maybe a few minutes late, but let me go ahead and open us up in prayer, and I'll give you a sense of the material that we're going to be covering today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course, Lord. I pray that the material will be clear, that it can be enjoyable, and that they can see that this is going to be a contribution that's going to help them to be better programmers in their future professions. Pray that you would also help them in their spiritual formation, Lord, that all of the times that they're getting a chance to be studying about scripture and all of the classes that they're looking at theological understanding will help them for both now how they can apply the things that they're bringing into their heart, and also in the future how that they can be leveraging biblical truth in their future. Give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, what we're going to do today is we're going to be talking about an application of recursion. And so we'll do a little bit of a high overview of this chapter, and then we'll get into the video notes. And then what I would like to do is have us start to get into sorting, and we have a couple of chapters on that. And so now we'll get a better sense of how we can be using this information that we're getting our arms around in some interesting ways that are extending what we're able to do with list with these other things. And you might want to just keep this in mind that we have list implementations, then we started to have all kinds of different related chapters, and we only get down to our next abstract data type that we're going to have in terms of a development is here for dictionaries. And so we have list, and then we get into this other variant sorted list, which is also a nice precursor for some of the things that we'll be getting a chance to see a little bit later in the course. So in this chapter, we get to be thinking about how recursion can be a simple solution to a difficult problem just by breaking things down in parts. That actually works quite well. And in the lecture notes, they talk about a poor solution to a simple problem. Maybe you've heard of the Fibonacci sequence, and so we'll talk about, at least in the lecture notes, what ends up being not a very efficient way of doing that. So the big O notation for that is really not very good at all. We'll also be thinking about the languages and grammars. We can be thinking of how we can be applying recursion to some interesting problems. We talked about going from infix to prefix or postfix. Those are stuff that we'll have. We'll also introduce something called indirect recursion. So you have one method calls, so method A calls method B, and then method C goes back to method A. So we can have this, what's called an indirect approach for doing that. And then we'll introduce this idea of a backtracking, that you try a hypothesis, you go several layers, and if it turns out that that's not the right one, then you backtrack and then you go to the next one. So sometimes you have to have multiple possible scenarios that you're engaging with. So this is something that's in the textbook. It's something called the Towers of Hanoi. The goal is to try and get all of these disks over here on number 3 with the largest one on the bottom. But this is a stack, and you only have access to the one that's on top. And so that's the scenario that we have. So it's this is an example where recursion shows itself to be a simple solution to this difficult problem. And so we could, instead of having like a stack of 3, we could break it down to a stack of 2 and a stack of 1, and make it more tractable. So that's something that we can see here. And so here we can just see the scenario of how we go about going from navigating from getting things from one to another, and within the rules of what's allowed for that type of a game. So I'm not going to go through that in detail. Here we see an example with 4. It starts out with us talking about 1 of 3. And so those are some possibilities. And so the basic takeaway is that we do it via recursion. Recursion is a powerful thing, and so there's classes of problems that it's a lot easier if we do it with a recursive approach. So this is just walking through, well, here's a solution, but the big O notation is going to be astronomical, and I'm not going to get into this in detail here. I'm going to let some of the video notes to give us some perspective on that. So we mentioned indirect recursion, and like I said, you have an example from a high-level theoretical point of view is method A calls method B, then method B calls method C, then method C comes back and calls method A. So eventually we get into this recursive loop, but this is something that can be difficult to understand and trace, but it does happen occasionally. And so that's something that we just wanted to make sure that you have an idea. So say you have evaluation and then validity of an algebraic expression. So the algebraic expression is either of two terms separated by a plus or a minus operator. The term is either a factor of two factors separated by a either multiplication or division operator. Factor is either a variable or an algebraic expression enclosed in parentheses, and a variable is a single letter. So these are all the possible things that we have to be doing, being ready for a general expression. And so that's where we can get into some of these issues where maybe we're going to have indirect recursion, that we're going to have to manage with all these different possible things. So this is where we can see that we can be going through this lengthy expression, and you break it down, and so that just gives you a picture of what that might actually start to look like. Then we have a couple examples here. Here is the first one. You can be thinking of a maze, and so you need to be getting from the entrance to the exit. And so, but we don't have the vantage point of seeing. For us, it's quite easy because we can see it from a different perspective. But if you're locked in a two-dimensional maze, you're just going to be seeing one thing at a time, and you're going to have to be making these decisions. I mean, at this point, I could either go all the way down here, or I could make this point here. And so you can see that we can have an example where we'd end up having to backtrack a couple of possibilities if we're doing an exhaustive excursion for all the different places in which we could be navigating as we're going through that maze. There's also a queens problem here. We see a four queens problem. When we have the video notes, it will be showing another example that's going to be larger than this. But for the ease of trying to have it in the lecture notes, this is what it would look like, where you can see all these different possible directions you could be going. So was there any queen? And then these other things? No. Okay. Well, then we have here. So the rules are laid out that we have to be thinking what is the best path for us to be solving this other type of a problem. So we're in this chapter, what we're doing is we're just getting a chance to see some different ways that we can be using recursion in some real useful problems. And so we're seeing some game possibilities as maybe an entry point to be thinking about that. Okay, well, let's go over to the video notes, and we'll get a chance to get a more in-depth perspective, and I'll go ahead and annotate some of these things a little bit as we work through it.
Palindromes are strictly the same from left to right as they do from right to left.
So we're not going to be talking about the Tower of Hanoi. We're going to be talking about another different type of thing, but just as a similar way of what we did that, we could be doing it with palindromes. And so they'll give us a sense of what it is, and then we'll get into how we're going to be using recursion to help us with that.
If we wanted to formally define this in the language, it would be all strings W such that W reads the same from left to right as right to left. What's more interesting is a formal Bacchus-Naur form grammar where we define palindrome as either an empty string, so a string that has no characters in it is a palindrome because it's the same either way.
So we're walking through this of how we in pseudocode can be capturing what is the essence of a palindrome. So Ada was an example. Maybe you've heard of the computer language Ada. And so it begins and ends with A. It has D in the middle. That's a short version of a palindrome that you can see how this would work.
Okay. A palindrome can be a single character. That's what the angle brackets with car in between means, is that our palindrome can be just one character, because if it's one character, going from left to right and right to left is the same character. Or a palindrome can be the character A followed by some other palindrome followed by the character A. So going from left to right, we have A, some palindrome that reads the same left to right, terminated by an A. Going from right to left, it's the character A, followed by a palindrome that's the same left to right as right to left, followed by another character A. And then we continue defining it this way for all the different characters in the alphabet. And the symbol character reads A through Z, lowercase a through Z, uppercase. And so if we take our time and think about this, we can see that this definition is recursive because it uses the word palindrome, or the definition for palindrome, in defining itself. For example, a palindrome is a letter A followed by a palindrome followed by the letter A. Well, what's a palindrome? Well, you go back to the definition and select one of the other options as you go through and you build your palindrome. If we want to recognize a palindrome, we can use this formula and realize that, okay, we have a base case here for success. A character is our base case. If we find a character, we don't do recursion. Also an empty string. So if we have nothing, we can consider that a base case also. Then for failure is if we're matching up left and right and they don't equal, then we'll know that we have failure also. So let's look at a quick algorithm here we can use to recognize palindromes. We'll take W as the string that we're being given, and our function is pal will return true if it's a palindrome and false if W is not a palindrome. Well, first we have our base case. If W is empty or it has one character in it, hey, we got our palindrome. We're all set. Notice that if we take one character from the left of a multi-character string and one character from the right, if the string has an odd number of characters and we continue doing that, we'll eventually get down to a string of 1. If our string has an even number of characters and we continually take one off the front and one off the back, we'll end up with no characters.
So you can see what's happening is we're defining a problem. Now we're working out how we go about breaking it down into easier digestible parts. So even that this idea here where we're defining a palindrome within itself, and it's recursive because so Ada, you could say that a single letter is a palindrome. So there's a palindrome within the palindrome. And we're going to be seeing now we're going to be having a general way of looking at that.
And that's the other base case here. So we have our two base cases. And so that's how we're going to actually recognize our palindrome. We first check to see if we have the first and last characters being the same. If they are, then we remove those characters and check to see if what's inside there is the same. Otherwise, we return false because the first and last characters don't match. So this simple algorithm will help us recognize a palindrome. If we have an empty string or a single character, it's a palindrome. Otherwise, we compare the first and last characters. If the first and last characters are the same, we know we have the potential to be a palindrome. In that case, we take out the first and last characters and look at what's inside and see if that's a palindrome. So we check is pal W minus the first and last characters. And we continue doing this repeatedly until either we end up with an empty string because we had an even number of characters, or a single character because we had an odd number of characters. Another interesting place to use recursion is with algebraic expressions.
Okay, so we very quickly mentioned this in the lecture notes. Now we'll get a chance to flesh this out a little bit more. And this would probably be something more generic, something that you will could likely be dealing with. Say, I keep thinking about developing a compiler or something like that with some of the things that we're starting to explore here. Or like when you're using Java, you're using Eclipse or something like that, it's constantly giving you tips about how your code is going.
You're used to infix expressions. This is where the operator appears in between operands. For example, the plus symbol is in between A plus B in this expression. There are two other ways to write expressions. Prefix expressions places the operator beforehand. So instead of having A plus B, we have plus AB. Also, we have postfix expressions. Postfix expressions are where we have the operator after the operands. So instead of A plus B, we now have AB, the operands, followed by plus, which is the operator. Now, there are some advantages to prefix and postfix expressions. For example, we don't have to worry about precedence rules. We perform the operations in the order they are in the expression. We don't have to worry about association. We don't have to worry about parentheses. In prefix and postfix expressions, there are no parentheses. And they're very simple grammars, very simple to program the evaluation of these. We'll see that.
So you can see these kind of advantages. This is exactly if you're going to be using a computational capability. If you do this conversion, it's going to be a lot simpler. And so those are the kind of motivations that they're starting to point out.
There's a very straightforward recognition and evaluation algorithms, which is important if you're going to write a program such as a calculator program. It's much easier to convert an infix expression into a prefix or postfix expression, and then evaluate the prefix or postfix expression.
So that's not an example of recursion. We're going to be getting into things here in a minute, but it's also still talking about this breaking down things into logical functions of what you want to do with your code.
So if we want to convert an infix expression, which we're used to, into a prefix expression, the first thing we do is we take each operator and move it to where the corresponding open parentheses would be. And then we just remove the parentheses. For example, if we had this expression where we add A plus B, that quantity, and then multiply the result times C, the corresponding prefix expression would be the multiplication symbol, the plus symbol, ABC.
So up to this point, this isn't the first time we've talked about algebraic expressions. We've talked about how, say, like a stack can help us, or some other things that we've been exposed to. Now we're going to see how recursion can be another thing that would help us out with this type of a problem.
Because we took out each of the operators and then placed it where the open parentheses is for that operation. To convert an infix expression into a postfix expression, we do something similar, except we move each operator into the position marked by its corresponding closing parentheses, and then we remove the parentheses. So if we have the same infix expression, to convert it to a postfix expression, we take each operator and move it to the closing parentheses. So we have A, B plus C times. So let's look at how we can recognize a prefix expression. Once we've recognized it, we can look at evaluating it. In this lecture, we're just going to look at a recursive algorithm to recognize prefix expressions. Here's a grammar for our prefix expression. A prefix expression can be a single identifier, such as A, B, C, D, some character that represents a variable, or our prefix expression can be an operator, which is plus, minus, multiplication, or division, followed by two prefix expressions. The prefix expressions can either be identifiers or they could be other prefix expressions. As you saw earlier, we had the multiplication symbol followed by the plus symbol and then two identifiers, and then followed by a third identifier. So that plus symbol followed by the AB was a prefix expression that we could evaluate and return up a level in the recursion. So the recursive algorithm here is going to be where we have the operator and then two prefix expressions. Now, these prefix expressions could either be just simple identifiers or other prefix expressions. That's what our recursion is going to help us resolve. So we can evaluate a prefix expression by first looking at that first character and removing it from the expression. Now, if this character is an identifier, what we do is we return the value of that identifier. We're done. Otherwise, if the character is an operator, we have the second definition of what a prefix expression is, which means that the two things we need to operate on are going to come following this operator.
So this is a nice middle step. We're developing the pseudocode here of how we're going to how we're going to do this prefix expression conversion.
So the next thing we do is we evaluate the next prefix expression. And then the second prefix expression, we evaluate that. And then we return the operation on those two prefix expressions. So either we return the value of the identifier, or we evaluate the two prefix expressions that follow and return the result of the operator operating on the results of those two prefixes.
So we have like a basis thing that's we could parse it down and get to this lower level to see how we're going to deal with this prefix expression. Okay, so that's the first one that we wanted to be seen on this topic. And so as we get into sorting and searching, what's going to be coming up next, I think you'll get a better sense of some of the things related to our course material, where that's going to come in, where recursion is going to be helpful. Okay, let's do this other one. This is now is going to get into backtracking, sorry.
Backtracking is where you search for a solution, and then when you reach an impasse, you back up and try a different route. Sometimes this is called depth-first searching. Recursion and backtracking can be combined to solve a multitude of problems that are very difficult to solve otherwise.
I don't know if any of you have been exposed to machine learning and stuff like that and deep learning, but that's going to be another place where you're going to get some experience with backtracking. If you've already seen it, then maybe this will help you get some sense of that. But we're seeing it's going to be going through a game per se to give us an introduction, rather than thinking through all the nodes in a neural network.
Such as searching a labyrinth of caves for a particular item, or just trying to find the best airline route between two cities. For example, you could begin at an origin city and then try every possible sequence of flights from one city to another until you either end up at your destination city, or you figure out that there's no route to get from my city to that city based on the current routes that the airline has. Whenever you find out that you chose the wrong city and there's no more routes, you can always back up and try a different way. Let's look at an example of that. Let's take the High Plains Airline Company, HP Air, and our goal is to figure out whether HP Air has flights that go from two cities. For example,
I can put this into a context. One of the things that we'll see here is when we get into trees and graphs and stuff like that, we're going to be seeing some examples of where whether if we're thinking of a road route or a plane, where they go from to the connections where they have hubs and stuff like that. We can see how we can be looking at all those possible scenarios and then pick the best one based upon the criteria that we're looking. Maybe it's the cheapest flight, maybe it's the fastest flight, maybe it's the one that has other kind of criteria that you could come up with.
We fly from city P to city Z. Now, here's a map of HPR. You could consider it a graph or a directed graph. Adjacent vertices are two vertices that are joined by an edge, and we have a directed path between each of the different cities. So these letters or dots represent our cities, they're vertices in the graph. And we have a directed graph because we can only fly in one direction along each of these lines. For example, we can fly from P to R, but we're not able to fly from R to P because the directed graph goes in the direction P to R. Let's do a recursive search problem. We're going to look for possible outcomes that we could have from our recursion. We could eventually reach the destination city, and hey, that would be that's a successful base case for us. Or we could reach some city, say city X, and there's no departing flights from that city. So that's a failure base case. In this case, what we're going to do is back up and try a different route from the previous city, and then repeat our recursion down that particular path from that city.
So this is giving us a strategy of how we can be doing searching, how we can be solving a problem by breaking it into smaller problems. So just thinking of that maze, we're now thinking of how we're going from some location to a destination. We're going to do it in an algorithmic form, and that's what we have here.
Another option is we could end up going around in circles on this graph, but what we're going to do to prevent that is mark each of the cities we visited so that we don't get these cycles. So let's look at our algorithm. We'd start at city P, and our goal is to get to city Z. We may try city R first, because it's fairly close. And notice we mark P, that's a city we've visited. So we don't come back to P, or when we come back to P, we know we've been there already. From R, we look at where we can go. Well, from R, we can only go to city X. So we go to city X. Now, while we're at city X, we see that we cannot go any further. So our base case is going to tell us we failed. We need to back up to the previous city and see where we can go from there. See if there are other routes, other cities we can go to. So we back up to R. But at this point, we've already visited all the cities from R we can get to, which was X. There was only one. So we back up again from R to P. Now that we're at P and we know we've tried R, let's see what happens if we go to W. So we go to W, then we try to go to S. We look and say, well, from S, we can go to T. When we get to T, we see that we've already visited W, which is the only city we can get to from T. So from T, we back up to S. From S, there are no more cities that we can try to visit. So from S, we back up to W. Then from W, we try Y. Well, at Y, we look and we say, okay, we've already visited city R, and that's a failure. So let's go to city Z. So we go to city Z, and we found success because we eventually reached our destination city.
So it kind of worked out, it is an exercise where we're trying to learn this stuff. And so we're kind of trying all these different things. And it turns out that the last one that we have is the one that gets us to the goal city. We might actually find it sooner than that. Notice also that we never made it down to the city down on the bottom here. But there isn't any way that you can get there from P. And so that's just an artifact of the way that it's laid out.
So that's an example of how backtracking could work to search through a graph or a labyrinth of caves or an airline route, as we did here, to find a path from where you are to where you need to go. We could write that down as this algorithm here. We have a recursive search algorithm where we start at our origin city and we have a destination city. We mark the city we're at as visited. If this is what we're looking for, it's the origin city is the destination city, we're done. Otherwise, for each of the cities we haven't visited that are next to the origin city, we recursively search based at that city, sending that city and the original destination city to the recursive call.
So we see the recursive call down here. Here is our terminate that we found the destination. We saw an example on the last slide where we were able to do that. So we always have a base case, at least one base case, and then we have calling into the same routine in the routine for us to be doing recursion.
Call. Another interesting backtracking problem is the 8 queens problem.
So we saw the 4 queens version of this in the textbook and in our lecture notes. This is going to be larger. And so I think this will help you to get a better sense of what this is all about.
This is where we place 8 queens on a chessboard so that no queen can attack any other queen. Now, queens can attack diagonally along both diagonals, and they can attack along the row and column where they're placed. One possible strategy is just to guess at a solution. Let's place a queen and place another queen, and just place them and see if we can make it work. Well, there's over 4 billion ways to arrange 8 queens on a chessboard that has 64 squares. So if we just want to randomly guess at solutions, it's going to take us a little while to get that. But we can make an observation. When a queen is placed, no other queen could be on the same row or column that contains that particular queen. That really narrows it down to about 40,000 different options, or 8 factorial different arrangements that we can use to check. Well, let's use our backtracking idea and come up with a search strategy that'll help us out. Our searching strategy is going to place queens on the board 1 column at a time. We'll start at the leftmost column, place a queen, then place one on the next column, and place one on the next column. If we find out that we have a column where there's no open space, in other words, if we place a queen on any of the squares in that column, she'll be under attack. We go back and change where the previous queen was placed. If there's no other place to place that queen, we'll go back and change the one before her that was placed. And we'll continue until we can place all the queens. Our base case will be there's no more columns to consider. We've got to the last column, we've placed our queen, and we've essentially solved the problem.
So you can see this is starting to get into a sorting thing. So you have certain criteria of how you're trying to have the relationship between elements. Here, where we have this queens problem with the kind of characteristics of where it can move, and so you're trying to avoid that. You could be doing something in alphabetical order or something like that. That would be a form of sorting.
The recursive step is going to be if we successfully place a queen in the current column, we're going to recursively look at the next column. If we can't place a queen in our current column, we're going to need to backtrack. So let's see what this looks like. Here's our chessboard. We're going to place our first queen in the upper left-hand corner. We've highlighted the squares that this queen can attack in yellow. We know that when we go to the second column, we cannot place a queen in any yellow square. So let's place her in the first non-yellow square. And then we mark with yellow where she can attack. And so now we're narrowing down the number of squares that we can place the next queen. We go to the third column and we repeat the same process. Okay, what's a square that's not yellow that we can place this queen? And we choose this white square to place her in, and we mark all the squares she can attack in yellow. We do that with the next queen. And now we're down to 2 squares for the following queen. And we place her in this particular square where she can attack these squares. Now, when we go to the next column, there's no open spot. Every square is under attack by a queen. So we've made a mistake somewhere. So we have to go back and remove the queen that we placed last and try in a different location. Well, there was one other square we could place her in. So if we place her there, she'll attack these squares. And then we have only 1 square to place this queen. We place her in that square in yellow, the square she can attack. We have 1 square for the next queen. We place her, and we're finally down to the last column. But again, there's no open spot. So we need.
So with this scenario, we see at least 2 examples where we got to a place where you can't go any further, so you have to backtrack. So we're seeing this algorithm that we have laid out this is, maybe there could be a more efficient algorithm. We're going to be talking about some algorithms and complexity and which ones perform better. But this is a straightforward thing that we're doing here. And so we're going to have to backtrack. In this case, like we did earlier, we're going to have to backtrack further.
We need to back up this last queen and remove her. And then we need to go to the previous queen, but there's only one spot to place her. So we need to go back again, remove that queen. Well, when we remove that queen, we realize we've already tried both of those squares and neither of those worked. So that means the queen before this one needs to be removed. And we'll have to remove her and try her in another square. Now we'll go mark the squares that she can attack in yellow and repeat this process. So you continue to do this and eventually you'll solve the 8 queens problem.
Okay, so the motivation for getting a chance to see that was to go through what can we see, what are the things that we can accomplish through recursion that are relevant to the things that we're trying to get our arms around. Okay, I'm going to just go into this next one on an introduction to sorting. And so there's in an interlude that I'll skip over at least for now. And so let's just get into talking about, well, what is sorting and where does that start to help us? And so here in this chapter, we have 3 different sorting approaches here. And so what you'll see in this chapter and getting into the next chapter, we'll have like about 6 different sorting strategies that go from fairly straightforward. And so the selection sort is easy for us to comprehend. The insertion sort is a little bit tougher. A shell sort is something where this is where you get into, you know, smart folks that are figuring out how to actually make things happen. And then the next chapter, they're going to be even more complicated, but perform better. And so we'll just start with this for now. So selection sort, it's an iterative selection sort. You use recursion to help us in the selection of where we're going to put things next. And we'll get a chance to be thinking about the efficiency. We'll do things similarly for the sort. And then we'll also thinking about the shell sort. We'll talk about the algorithm and talk about the efficiency. And then we can have the information to do a comparison across the board. So we can see sorting is a relatively straightforward concept. If you want to put things in alphabetical order or numerical order. So this is how it would be. So we have to, everything has to be comparable. That's something we're going to see as we get into this. And so there's going to be another criteria that if we're talking about some generic type, that generic type, there has to be some way of comparing one with another. So sorting an array is usually easier than sorting a chain of linked nodes. And so maybe keep that in mind. This might help you to be steering in one direction or another for implementation. And the efficiency of a sorting algorithm is significant. So here's an example of a selection sort. And so basically, you're trying to go from small to large. And so you scan here which one's the smallest, and so you swap those. And so you just put the big book over here and the little book over there. And so now you got the first one. Now you have to do for the rest of them, except for the first one. And so you're going to keep repeating that. So that's the general strategy for this. So we see that first swap. And so then we're going to do another swap. So we know that the first 2 are sorted. Then we're going to do this third swap. We know that the first 3 are sorted. Then we're going to do this final swap. And then we got everything in its numerical order from smallest to largest. That just gives you an idea how that would work. So we have the pseudocode that describes how we go about that process. I'll reserve the video notes for next week, but we can just think about this here for now. So that's the general pseudocode. And so you have the sample code, and probably if you wanted to do a sorted list, this is going to be the one that's going to be the easiest to comprehend. It's the one that's going to perform the least, but you can just get a chance to, you're going to be following this kind of an algorithm that we show here. And this is what it would look like for putting that into code. You also have this comparable, and this is, you get into the syntax that is required. So you have the angle brackets and the question mark, and then you use the super and the generic type T. So this is what we see that we're going to be having with that. And so here we see the sort array, just the method that we would be using for that. We have some other things that the way that they do their code, they tend to have a lot of private methods. And so here we have a private method that we're getting a chance to walk through here. And so this is a class for sorting array using a selection source. And so this is just gets into the details of how we make all that happen. And here is the swap. And so let me just do a scan here. So the swap is the actual thing that does this movement. And so we're breaking up this code into, first of all, figuring out if we need to do a swap, then actually doing the swap. So we're seeing this one at a time. So we have the comparable. So this is where we need to figure out whether or not we need to do something. And then we actually have the code that actually changes the order where they are in our array. So that would be doing things in an iterative approach. And now let's think about how we would do these things in a recursive approach here. And so we have the general algorithm. And so selection sort, we need to have that is called within here. And so this is the recursion that's within the algorithm itself. So guess what? We have this big O notation of n squared. That's a lot of computations, and so this is not going to be very efficient, but you can maybe just looking at this, you can be seeing about here. So you do this, then you have n1 remaining that you have to sort. You do that, then you still have n minus 2 that you need to sort. And so that just gives you a rough idea where these large numbers are going on that you have to do. It takes n swaps for each iteration that you're going about doing that. So so we have the selection sort, and then the next one is a selection sort. So we'll just go through this same thing again, but now just be thinking about it for this insertion. And so basically what we're doing is we find one that's shorter, and then we're just going to push everything down. And so then we're going to put it there. So it's like if you have a stack of books, you have to put it down. But if we're having an array, that means you have to move all these array elements over one so you can be sticking that in. And so that's just the general strategy for what's going on. So you have these things that are sorted, then you find, okay, this one's needs to go here. And so those are ones that, but the thing is, since these are now sorted, it's going to take less effort for you to be putting this in the right place. And so gradually, as you go down this stack of books, each of those scenarios is going to be easier than at the very beginning. You have to scan through all the books to figure out where it needs to go. So this is the general strategy of what you're finding. And so here we have several of them are sorted, and we find that 3, it needs to be going over here. So we have to move things one at a time. We have this item out temporarily until we get it to its right place, and then we stick it in that place. And so this is now just giving us a better sense of what it would look like from an algorithmic point of view. And we're just gradually going through that whole process, and it gradually gets easier and easier because the ones over here are all sorted. And we saw that with the stack of books. I was trying to give you a sense of how that works. Here's the general algorithm again. And so this is an iterative approach. So we can see how that works, the pseudocode. And then we have the recursive approach, the insertion sort. Well, I'm not going to scan of this, but so we have insertion sorts. There should be insertion sort here someplace. So we'll just and then we have here is the code for doing that. And so we have this comparable thing, the same thing we saw for the iterative approach, the things that we did for the first version of a sort. And then we do those these two things. We have a recursive call back to this, and then we have this, but we do it for one element less than what we did before, and then we have insert in order. So this is a private method that's not shown here. So this code looks deceivingly simple, but there's some other lines of code that are there. And so here is this insert in order that we're starting to unpack here. We have an algorithm for that. We saw this roughly before, but now we're getting a chance to see things at a little bit lower level of how it actually works. Here we have the recursive insertion sorts, the insertions for the insert in order piece, and then we have the insert in order piece there that's within the code. You could probably see that this would actually be a little bit easier if we had it with a linked implementation. So an insertion source, maybe a linked implementation might be easier. So you can just, instead of having to moving everything out of the way, you can just change what things are linked to. And so that might actually make it a little bit more straightforward. And here we're seeing things. I'm trying to give a sense of what we're going to be doing in terms of the parameters and the variables that we would be making sure that we include to make sure that that's correct. So we're going to have the private class node. That's something that we've always had to do with a linked implementation. And so we're getting a chance to see that. Here is some more details. The class has an inner class node with set and get methods. And so here we're seeing some of that laid out for the linked chain implementation. Here is what it would look like for the actual insert sort. And the third and final one, this is going to be more complicated, but its performance is going to be better. And this is this final one that we'll just call it a day after this. I'll just go over to Eclipse just for a few minutes. So algorithms so far have been very simple but inefficient. The more sorting an array is, the less work insert in order must do. So the improved insertion sort was developed by Donald Shell. So basically, we're just kind of having a suboptimal per se of like, well, let's just swap a few elements. It may not be the smallest element, but we kind of do it in a one step at a time. And so we can see that, well, we start here. Well, 7 is smaller than 10, so we swap those. And so this is what we start to do things at one step at a time. And we're going to may not seem so intuitive, but this is actually going to perform better rather than having more of these exhaustive approaches that we saw for the first two sorting strategies that we had here in this chapter. So I think it'd be a little bit easier to capture that in the video notes, but so we can see for these first two, The selection sort across the board, it takes n squared, big O notation n squared for the insertion sort, at least for the best case, it's better. And for the shell sort, it's down from 2 to 1.5. So it is an improvement, but there's a little bit more we can do beyond that. Okay, well, let me just do a quick thumb check. You guys were able to track what I talked about with the practical applications of what we can do with recursion for things that we're doing. And then we got a chance to get an introduction into sorting. You guys tracking with what I presented there? Okay, good. If I end up going too fast, you guys can let me know. We can always spend some more time on this material, but we've got a lot of stuff to cover in the class, and so I'm trying to see if I can be using our time well for when we're together as a class. Okay, so we talked about on Tuesday this idea of searching. And so here are a couple examples that we have here for some sample code that we can be thinking about. Let me just make sure that I'm sharing my screen. Okay, stop sharing. So this is just, so let me do so here I have a chain search. And so that would be a linked implementation, and then we have an array search. And so maybe I'll just try not make things too difficult. I'll just do one at a time here. So this isn't using the convention that we have been doing up to this point where you have an interface, but this is just some sample code that's trying to have us get a better sense of these different types of searching approaches and what's necessary to make it all come together. And so first we have an array searcher. And so we have our class that actually does that process, and then we have our driver. And so let's just think about this first one, maybe just to be on the safe side, I'll close this one. So here we have the array searchers. This is a class of static methods for searching an array of objects. The object in a sorted array must be comparable. So that's something that's worthwhile for us to be thinking about. So I have the array search, and I'll open up the driver here as well. So here, this is following what's in chapter 19. And so we have the class array searcher. This is what this .java file is about. And so we have a couple of different methods. And so first is in unsorted array iterative. So we have an iterative approach to doing a searching mechanism here. And so what we do is we initialize the Boolean return to false and the index to 0. And so as long as it's not found, so this would be still being true, and that the index is less than the array length. And if we're going to continue to do this built-in function here for an entry, does it equal an array index? And so if it does, then it's going to be true. And we keep doing this until we get this is to be false, this conjunction here. And if there's multiple entries, then we just need to have it that it shows that it's true. For one, we go out and we finish that, and we return the Boolean. And so we're looking for a search an unsorted array for an entry. So then in segment 16.9, so you can be following this in the textbook, this is searches an unsorted array for an entry by calling a recursive private method. So This is an iterative solution. This is a recursive solution here. So we then do a search that is one level less than what was done before. And so that's what we're seeing here. And so we then have to go to search. Yeah, this is always trying to go for somebody's code and quickly be able to find stuff. Okay, so here is a private method search. So this looks deceptively simple, but it's calling a private method here where it does things in the things that it's looking at that each time it's going one level less and what it's going to be going in terms of that search space. So here from segment 19.13, it searches a sorted array for an entry by calling a recursive private method. So we're just seeing a couple of possibilities here that we could be utilizing here within this array searcher that it could be leveraging. And so in unsorted array recursive, in unsorted iterative, and then we have here's an in-sorted array recursive. And so we have various things that we can be leveraging. So there's various methods that are available for us that we can be looking at a couple of things that we could try. And so here we can be looking at those three possibilities here. So we have the iterative sequential search, a recursive sequential search, and then a recursive binary search of a sorted array. So iterative, and then we have two recursive possibilities. We haven't talked about a binary search yet in detail. So binary, it's one or the other. So we'll have something called a binary search tree. And so this is something that's coming up that is a helpful feature. It's either true or false. It's either one or the other. And so this can be another example of something that can be helping us to get some improvement in our performance of our code. Does that make sense? You guys following what I had there? Just you can give me a thumbs up response if that's making some sense. Okay. So and then for we'll go through this a little bit faster. So the other one was an array implementation. Here we have a linked implementation. And so maybe what I'll do is I'll just do a quick scan here. So we have something similar here. We have an iterative sequential, recursive sequential, and iterative sequential. So we have three different cases, slightly different methods that are developed, but this time we're doing things with a linked implementation. So we're going to have a private class node. So let's see where they put that. So our private class node is down at the bottom here. And then we have each of these three different approaches that we have for doing our searching here. which is stuff we have. Well, I apologize. We actually haven't talked about chapter 19 yet, but we did get a chance to talk about iterators. And so some of this is a little bit more advanced, and so we'll be coming back to this when we get to 19. I was trying to find something that was relevant for some of the things that we've talked about so far. And so sorry I didn't catch that before I went through these examples here, but anyway, so you're going to be seeing some more of this as we go, but I think I'll just go ahead and call it quits for going over that material. I'll just pause for a minute or two to see if there's any comments or questions that you guys have. Okay, thumbs up. I'm going to take it. That means that things are looking good, and that's good. If some of you are having some challenges, just please feel free to reach out to me, and we'll continue to have that dialogue. Okay. Well, anyway, the Lord bless you guys. I hope you have a wonderful rest of your day, and I look forward to seeing you next Tuesday. Take care.
Thank you.